picture, in this case, lab results, paint 1,000 words, right? Deformation versus tau. For a given imposed stress. Notice that. This is what we measure. We also measure this. We impose this. So this could be, let's say, 30 kPa. So for 30 kPa that we impose on the test, this is what the plot looks like. Okay, so you can have different shapes of curves. In general, what you have is something like this, or maybe something like this. Okay, now this could all be relative, right? You could have, for example, something like that. Okay, but the main, regardless of how high, let's say, the stresses are, the peak stresses, the highest maximum stresses are, the general shapes are no peak and then peak, followed by post-peak, meaning a decrease. Okay, so let's draw that one again. Those two. This is deformation. That is the horizontal deformation. And this is, the shear stress. These are two tests with a given sigma. The sigma is 30 kPa, for example. Okay? This is one test for one soil, and this is another test for another soil. Or it could be the same soil, but with a different void ratio to begin with. We'll talk about that later. So here we have a situation, again, where we have plotted the results of two tests. Soil number 1 exhibits a peak, and soil number 2 doesn't exhibit a peak, just because they are different, tested under different conditions, etc. Meaning the void ratio, for example, is different for them, or they are just plainly different soils made of with different grain size distribution, etc. That doesn't matter for now. We'll get to that later. Okay, now what is the importance of this plot? There are quite a few things that we can consider important, but perhaps the most important is that this is the plot that is going to tell us or give us the opportunity to pick what we call failure. Okay? Now, you may say, well, failure is when the block starts moving. I'm sorry, you could say block is the moment when the top of the box, that is the top of the specimen, begins moving, right? And that would be intuitively, if you are comparing to this condition here, that would be a good answer or a good observation. But we have to realize that the soil continues to offer resistance during its deformation, whereas a block, the minute you start moving it, the coefficient of friction drops to the dynamic one, static to dynamic, and there's less force required to continue to move the block than there is to push it or to begin to move it. So in this case, deformation begins immediately. Look, the deformation is plotted here. Deformation begins immediately after the test is started. So what we need to find are characteristic stresses on the failure plane, shear stresses, that are most descriptive of what we call failure. So let's look at soil 1, or let's look at soil 2. We would say, okay, soil 2. The soil is deforming, and it is continuously offering increasing resistance, right? To the point where the resistance becomes constant. And the highest measured is this constant value. So what we would say is, okay, let's consider, just like, a person that can do 63 push-ups, that person has that as the maximum, therefore that's what defines their strength, not 30 push-ups, 63, right? We could say, okay, what defines the strength of the soil is the maximum shear stress that can be supported along that failure plane. Okay, then that would be this value. And that is what we call the strength. That is the strength of that soil, soil number 2, which is the shear stress on the failure plane at failure, that is recorded as the maximum for that soil, again, when it's loaded with this sigma. If you change the sigma, the soil response changes, and we'll get to that later. Now, what about soil 1? So this is the strength of soil number 2. Soil number 1 has a peak value, so the resistance increases all the way to this value here, and then it actually drops to a constant value. Okay? So, based on the previous argument, you would say, oh well, the maximum resistance, that is the maximum shear stress on the failure plane recorded, is this value. So I'm going to call this shear stress. I'm going to call it S2. Oh, sorry, S1 for soil 1, right? And that is a correct and reasonable selection for the failure point. Remember that failure defines strength. Now, a little bit more thinking perhaps would tell you, wait, so if the soil deforms in the field, there will be a point where it reaches, it offers its maximum resistance along a failure plane. But then if the soil deforms more for some reason, then the resistance drops to this value here. So which is the strength that I should rely on? Well, this one is great because it's high, but I know that if the soil deforms more than this amount, in general, this should be a strain, but we cannot plot really strains with the direct shear test because of another reason. But basically we can say, look, if the soil deforms beyond a certain, deformation or value, the strength decreases. So let's be conservative and select, again, this constant value as strength 1. Okay? And that is also reasonable. In fact, both strengths are reasonable. I would say more so what's called the critical state strength. Okay, that is more conservative. If we select this point, we call this the peak strength. If we select that point, or any point along this constant behavior here, that's called the critical state. And what happens there is that there is no increase or decrease in resistance along the failure plane. Okay, and that is called the critical state. In this case, there's no peak. There is only the critical state, and that is the highest measured. So we call this one also the critical state. Okay, so going back, look, we said, and you have this in your notes, we said that we were going to measure the strength, divide by the applied force, which in this case is the weight of the block, to back calculate this so-called strength parameter. Okay? Here, we've done the same thing. Here, the middle step is that we actually have to get this plot and define what the strength is, based on the way the plots are, right? Basically the curves. So for soil number 1, we have two strengths. This one and this one. We can select which one we want to use for design. Okay, and in this course we're going to use always critical state. And for soil 2, we have the critical state only, so that's the one we select. Now we're going to essentially divide by the sigma, which is the applied imposed stress, to determine our mu. See that? Just like block on plane, soil on soil, soil on soil. Okay? So this is the general understanding or concept of the direct shear test. Now we're going to get a little bit more into it in terms of the detail associated with what makes the curves look the way they do, and actually how are we going to calculate this and another parameter. In fact, we're going to change this mu into something else, and we'll get to that in a second. Not in a second, I meant in the next video. Okay.